I'm Vishal Chakraborty. I'm a PhD student in the Computer Science and Engineering department, and I'm going to talk about possible winners on partial chains. My research falls under computational social choice, and it's in the confluence of computer science and social choice theory. Social choice theory dates back to 15th century, with pioneers like German philosopher and theologian Nicolas of Cusa and French mathematician Jean-Charles de Borda. ComSoc uses algorithmic concepts of computer science to study two things: election mechanisms and fair allocation of resources. My research falls under election mechanisms and manipulation. So let's look at an example. Imagine you and your friend are going to vote in a local election where you need to rank all candidates from most favorite to least favorite. There are three candidates on the ballot: Lizzie, Bernard, and Don. And you indicate your ranking of these candidates. However, your friend is having some difficulties. They are not sure how to rank these candidates. However, they know that Bernard is their most favorite candidate. In my research, I'm interested in these incomplete ballots. So the election is done and the votes are in. Lizzie's camp wants to know if Lizzie can win the election. More precisely, they ask the question if they can complete the incomplete ballots in a way which makes Lizzie the winner. Formally, this problem is known as the possible winner problem. It was introduced by Koniak and Lang in 2005. So let's take a look at what we are given. We have a set of candidates or alternatives. We have a set of incomplete votes or ballots, and we have a scoring rule. Let's take a small digression and understand what scoring rules are. Simply put, scoring rules are a way to assign points to ranked alternatives or candidates. Simple majority is perhaps the most commonly known rule. There are other important rules. The first one is plurality. In plurality, the first candidate gets a point, and all other candidates gets no points. The next example is board account. In board account, say there are M candidates. The rank 1 candidate gets M points. The second ranked candidates gets M-1 points, and so on. The last candidate gets only 1 point. Let's look at a quick example. As you can see, each row on this table represents a rankings of the candidates available. The rank 1 candidate gets 1 point, which is in green, and the other candidates gets no points, and the points are in 0. We compute the total number of points made by these candidates. And the winner is the candidate with the maximum number of points. As you can see on this example, the winner is Lizzie with 2 points. Now let's go back to the possible winner problem definition. Recall that we had a set of candidates, a set of incomplete votes, and scoring rule. Given these, we asked the question, is candidate C a possible winner or not? In the example we started with, Lizzie was this candidate C. So my work is on possible winners on a special kind of incomplete vote called partial chains. What are partial chains? Think of Netflix. Any user have watched only a finite subset of all the movies available on Netflix. And so they can rank only these movies which they have watched. From Netflix perspective, this ranking is incomplete. Such a ranking is called a partial chain. In my work, I provide a complete classification of the possible winner problem on these special kinds of incomplete orders called partial chains. In particular, I classify that plurality and veto scoring rules are computationally easy. But for all other rules, the possible winner problem on partial chains is computationally difficult. Computationally hard, NP-complete, these are technical terms, but for now, we'll just stick to hard. Now, the next logical question is, you have proved that a problem is hard. What's next? Well, one of my ongoing work is how to solve this difficult problem in the most efficient way possible. Now you might ask, why are we talking about this? What makes this relevant? Well, let's conclude the talk by seeing some applications of the possible winner problem on partial chains. Imagine now that instead of human beings, the candidates are movies on YouTube, restaurants on Yelp, and products on Amazon. And the voters are simply the users or the subscribers on these websites. As you can see, the possible winner problem shows up frequently in the e-commerce, entertainment, and service industry, and thus it's extremely relevant today. Thank you for your time.